And here I just made a very schematical representation of a G-block, having this buckled like an accordion, the instrument you can play on, you know. Yeah. And this block have what we call a cavity, and inside here you have a strong binding of calcium. But not here, not here, not here, but inside here. So let's look a little bit more about the calcium binding. Because you know already when you add calcium to alginate containing G-blocks, the alginate form a gel. That you can do by dripping alginate solution into calcium. And this is what we think happens. Here is the alginate in solution. For instance, sodium alginate. And this buckled chain are the G-blocks. These are then the M-blocks or the Mg block. They are not involved in the gelling. When you add calcium, the calcium binds to the G-block, and at the same time it brings together two G-blocks, like this. So the chains get connected. Different chains get connected, but only in certain places where you have a G-block. Between the G-blocks, the alginate wants to be dissolved, but the G-blocks wants to go together. And this is the way the gel is formed, by connecting the chains in a few places. If you add more calcium, and also wait a little, we can observe actually that these structures tend to grow, associate. This model here is often called the egg box model. You know what I mean by egg box model? Just like in the supermarket, when you buy egg, it's in a box like this. So it has been referred to as egg box model for many years. So I will give you a small exercise, a little to think about. So this is the question. Alginate forms gels when calcium is added. What about other cations? Can we make gel with hydrogen, helium, lithium, beryllium, boron, carbon, and so on? I'll give you 2 minutes to think about that, and then we go on. Are there some suggestions? What do you think? Because there are other cations that do bind alginate, but which one? Okay. There are quite many cations that bind alginate. So I'll give you 1 minute to think about it. So a good idea is to look, where is calcium? It's here. That you know, maybe from before. Together with magnesium, these are the alkali earth metals: beryllium, magnesium, calcium, strontium, barium, and radium. And these are the alkali, no, what are they called in English? Oh, sorry. For the moment, I forgot the name. The lithium, sodium, potassium, rubidium, and cesium. The truth is that sodium does not gel with alginate, because if you take sodium alginate, it dissolves in water. No gel. And no gel with lithium, and no gel with potassium. Nothing happens here. Beryllium, I think, I don't know exactly. Nobody did this experiment, but magnesium alginate does not really form a gel. But strontium and barium does very well. So in fact, in some cases we can add a little bit of, for instance, barium to strengthen a gel. It has been done. And this is because these cations have the same charge as calcium. But they are getting bigger, but they still bind very well to alginate. Of course, in this region there are no cations, but for instance, chromium 3+, manganese 2+, iron 2+ or 3+, nickel 2+, copper 2+, zinc 2+, they all bind to alginate and form a gel. Also mercury and so on. Lead, definitely, as long as it is a salt. So many other cations bind alginate. But you wouldn't use a mercury alginate for biomedical purposes, would you? So better stick to calcium. So the next step is to study the properties of the gel. And one question is what many people call the gel strength. Gel strength is a very inaccurate term, but what they usually mean is elasticity. So one of the simplest ways to characterize a gel is to use a gel compression, simply by squeezing together the gel and measure the force. And for that, you can buy a very simple texture analyzer. So we make a gel cylinder, and we apply a force, observe a change in dimension, and make a simple plot of the force per area, and this should be the relative compression. And this initial tangent is called often Young's modulus and has been given a symbol E. And one of the important results is a study where we studied different G-block lengths and tested the elasticity. And this is a very famous figure showing that as the G-blocks get longer, the elasticity of the alginate gel becomes higher. Here, for instance, 0 G-blocks, no gel strength. And when we come to about 10 to 12, it seems to level out. And therefore, alginate with long G-blocks are very interesting commercially. And that is why the industry separate the stipe and the leaf. Because in the stipe, we have this type of alginate. In the leaf, it's a little more like this.